Good morning, friends. This is Mrs. Masters. We are going to talk today about tangents to circles and two big theorems that you need to know about tangents as they apply to circles. So we're going to start off with a little bit of review of some vocabulary that we discussed previously in class. First off, I'd like to review what is a tangent. So if you remember, a tangent is a line that intersects a circle in exactly one point. So line L here is tangent to circle S, and it is tangent at one point, at point T, where they both intersect. Right, so it's a line that intersects a circle in exactly one point. We call that one point where they intersect the point of tangency. And then there's this unique thing that happens at the point of tangency. If you were to draw a radius from the center of the circle to the point of tangency, so in this example, I've drawn line segment ST to represent the radius of circle S. Then we're looking at a situation where we have a perpendicular relationship. So there's a relationship between the tangent line and the radius that it is perpendicular at the point of tangency. So that's our first theorem for today, actually, is that it's perpendicular at the point of tangency. And we'll use that to solve problems in the next example here. A couple other vocab terms, common tangent. What that means is that you have two or more circles that have one line that is tangent to both. So one line tangent to two or more circles. This situation gets really interesting. I would encourage you to explore that. Why don't you draw some circles on a piece of paper? Draw different size circles, draw them in different relationships to one another. Maybe they're concentric, maybe they're intersecting, maybe they don't intersect at all. And can you draw a line that is tangent to both of those circles in those different relationships? And kind of explore that. And how many tangents can you draw for each of those scenarios? So there's some interesting questions there. More time to explore, but that's kind of an extension activity maybe we'll look at later. Secants we're not going to talk too much about today, but I do want to just put that vocab term out there for you. Remember that a secant is a line that intersects the circle in 2 points. Contrast that to a chord that we talked about. A chord has a line segment, right, with endpoints on the circle. The secant would be the line that contains the chord. Okay, so it extends forever in 2 directions, being a line, so it goes outside the circle as well. All right, so let's dive into some examples real quick. We've got 2 for you. So WE is tangent to circle D and solve for X. So if we know that that is tangent, we should also recognize that we have this right angle relationship happening. So here's my point of tangency, right, where the radius DW is tangent at W, and WE is my tangent line. So that's a right angle. So now if I'm looking, I have 3 sides and a right angle, so I've got a right triangle here. So I'm going to use Pythagorean theorem to set up and solve, keeping in mind that opposite the right angle, this segment right here is my hypotenuse. So since that is my hypotenuse, I'm going to set up an equation to solve that puts this side by itself. So then I would have x squared plus 24 squared would be the hypotenuse, which is x plus 16, quantity squared. Be careful when you square this quantity, folks. That's where we'll see a lot of mistakes here. Remember, that's a binomial times a binomial, so you got to multiply it out. Use FOIL if you need to, or use your patterns if you remember your perfect square patterns from Algebra 1. And then you can see that your x squareds, when you subtract them from both sides, they're going to cancel out. And you'll just be left with the linear equation 576 equals 32x plus 256. Subtract your 256 and divide by 32 to solve that x is 10. And you can check. This would mean that we have a circle or a circle with radius 10. The tangent segment is 24, and then the whole piece would be 26 here on the hypotenuse. So 10, 24, 26. That's an extension of a 5, 12, 13 Pythagorean triple. So yeah, that checks out. It's good. Our second theorem for today talks about what happens when you have 2 tangents to one circle. And if those 2 tangents to that one circle intersect outside the circle, we call B this common exterior point. All right, so that would mean that the segment AB and CB are congruent to each other. So two tangent lines intersecting in a common exterior point, then the distance from the point of tangency to the common exterior point on those two tangent lines is going to be congruent or the same. And we'll use this to solve problems as well. So let's look at a quick example. So if we have that A and B are tangent here to circle Z, then we can say, hey, they have this common exterior point. So that must mean that I have two segments that are congruent to each other. So AC is congruent to BC. So AC is congruent to BC, which allows me to set up an equation that I can solve. 3x plus 2 would have to equal 4x minus 3, and we can solve that. All right, so those are our two big theorems for today. I encourage you guys, pause the video, go back, watch it again, try the examples on your own. That's the beauty of a video, is you can always pause it. And then if you still have questions, feel free to shoot me an email. Make sure you ask those, okay? Have a great day. Thanks for watching.